Good afternoon, everyone. I'm Sultangali Arzykulov. I'm from Nazarbayev University. Thank you for the invitation to TÜBİTAK. So I had good experience from yesterday. Now, let me start my TED talk. So the topic is going to be about beyond 5G, exploring next generation technologies for 6G wireless communication. Before I dive into the research part, let me give you some brief introduction of our university. So Nazarbayev University, established in 2010. So as you can see, it's a very new university. It's located in the capital of Kazakhstan, in Astana. And this is the first university which started teaching only purely English. So we have approximately 5,000 undergraduate and postgraduate students. And we have around 400 professors from worldwide, and the ratio of international and technical professors is 70-30. So now let's go to the research part. So let's start talking about road to 6G, how we came to 6G. And everything started from in the early 80s. So we started with 1G where our mobile phones, they only have this basic voice and text services and internet. Then we came to 2G, where in 2G we started using digital communication by processing digital signal. Then in 2000, we had access to 3G, and by having 3G, we get access to internet in our mobile phones. Yeah, this is how it started. Still, the quality, the speed of internet is very low, but at that time it was very advanced technology. Then, in 2010, we had 4G. Now, 4G actually revolutionized the many technologies. So, right now, if you see your mobile phones, smartphones, gadgets, many applications, they are so advanced because of 4G. Yeah, so like Instagram, TikTok, all social media, all delivery services, all taxi services, they work this nice because of 4G. So right now we are in the era of 5G, where we get ultra high definition 3D data. So data is everywhere, massive connectivity of devices, and of course 5G is very advanced up to now. However, we're trying to move further, and now we're planning to explore 6G in the upcoming 10 years, 20 years. So actually, 6G is advanced 5G. Whatever you have in 5G, high data rate, extreme capacity, coverage, we're making them up to next level. So before we start talking about 6G, now let me provide some feedback, some history of 5G and what kind of requirements we have in 5G networks. So first of all, 5G is about high capacity, high data rate. 5G, you should have more than 10 gigabit per second data rate. This is the peak maximum one, or at least 100 megabit per second whenever we need. And also, 5G is about connectivity. It said that 1 million devices should be connected per kilometer square. So this is related to IoT devices. And also, besides connectivity, it also should be very power efficient. 10 years of battery. So it means devices, IoT devices, let's say, can use a battery without changing for 10 years. In this case, it should be either very power efficient protocols or wireless energy harvesting. This kind of stuff should be connected to 5G. And on the other side, in 5G, we should get very low latency. The latency should be below 1 millisecond. And at the same time, we should get very reliable communication by having 10 power of -5 end-to-end outage probability. So this is a requirement of 5G. If you satisfy all these requirements, we can get extreme mobile broadband, we can get massive machine communication, and the critical machine communication. Now, even though 5G networks have improved latency and speed, 6G is going to bring it to advanced levels, even higher levels. And now we start a journey from 5G to 6G. So what are the requirements for 6G? First of all, extreme high capacity or extreme high data rate. So as you remember from the last slide, in 5G we have 10 gigabit per second peak data rate. In 6G it should be 100 gigabit per second and 100 times higher capacity. Then 6G also should guarantee extreme coverage, and this gigabit per second coverage should be everywhere, not in like terrestrial, also non-terrestrial communication. Also new coverage areas should be explored like sky, sea, space, etc. And also 6G should be about extreme low energy and cost. And one of candidates for 6G is going to be millimeter wave and terahertz frequencies. And to afford this kind of devices, we need very efficient hardware. So besides these characteristics, also we have extreme low latency. In 5G we have 1 millisecond, but in 6G it should be 0.1 millisecond latency. At the same time, extreme high reliability, so ultra low latency phenomenon should be activated here as well. And at the same time, the network should be secure, private, resilient. And the last one, but not the least one, is extreme massive connectivity. Once in 5G, we had 1 million connected devices per kilometer square. Here is going to be 10 times higher, 10 million devices per kilometer square. And at the same time, it should have sensing capability. It should have high precision positioning in centimeters order. So all of these are requirements for 6G. And the 6G right now is in initial stage, in research stage. So actually, how in our group we see the research roadmap for the 6G. First of all, from our side, we try to implement some analytical solutions for the problem. So we use information theoretic approaches to find the fundamental limits of upper bound or lower bound of the system. Then develop new designs that may achieve these limits. So after we identify analytical solutions for the problem, we implement optimization methods, different kinds of algorithms. So here we use the analytical knowledge that we found before and implement in the optimization part in order to accelerate the optimization procedure. And then the last stage is to use some practical experiments. You found analytical solutions, you optimize the system now, you need to verify all your results through some practical measurements. Regarding 6G, so we saw some requirements for 6G, how we can research it. Now, 6G is about extreme, yeah? So you have extreme data rate, you have extreme coverage, you have extreme latency, etc. And it's not going to be one technology that can support all these requirements. Therefore, 6G is about symbiosis of several advanced technologies. And there are many candidate technologies that can be used in 6G. So I can provide some of them. The first category is about spectrum management. And the best candidates for this category is first terahertz communication, where we can get very high bandwidth and low latency. And second is millimeter wave frequency that also provides high bandwidth. At the same time, by using millimeter wave and the terahertz communication, we can get access to small antennas. So if we're going to use MIMO antennas in our mobile phones, smartphones, millimeter wave and terahertz can get access to these tiny antennas in order to make the device very compact. And then also regarding spectrum management, we have dynamic spectrum management techniques such as conuk radio. And as you remember, in 6G, we said we're going to have 10 million devices per kilometer square. So now, all these devices will use the same spectrum band. And the proper spectrum allocation or spectrum management is vital in this scenario. And there's kind of dynamic spectrum management or conuk techniques can help us to solve that problem. And then also we have advanced networking technologies such as configurable intelligent surfaces, where we can use programmable surfaces that can optimize wave propagation to improve the signal strength and spectral efficiency. Also, we have integrated communication and sensing method, where the same hardware can sense and provide communication to the users. And also the last category is about artificial intelligence and machine learning. This is an unavoidable technique that's going to be used in 6G because we need to optimize many parameters. We need to schedule, we need to allocate the resources in a very efficient manner. And here, the help of AI is very important. And also, digital twin technologies play a very vital role because in this kind of methods, we can copy the real world into the digital world, and we can do all optimization, we can do all experiment there in a cheaper way. Then these results can be applied to the real world. So these are just some technologies that can be used in 6G, but there are a bunch of them which I didn't mention. So in our research group, we actually work with some of these technologies. So we have a research direction on unmanned aerial vehicles, where we use UAV to relay signal, or we use it as a flying base station to solve some temporary problems. Also, we have research on reconfigurable intelligent surfaces and also in full duplex communication. So this full duplex communication is also a solution for spectrum management. Because we can transmit and receive the signal at the same time, and at the end of the day, we can get twice bandwidth. And also in 6G, I thought that security is very important. And there's one method called physical layer security, which can provide security to system in physical layer. This can be used as an initial approach for higher level security in order to provide extreme secure communication. Also, we have research on cognitive radio and then on orthogonal multiple access, which is multiple access techniques that can provide massive connectivity. Then other research that I'm not going to mention in the lecture in these slides is fluid antenna systems, wireless energy harvesting, and integrated sensing and communication. So now let's start. Let me just go briefly on some directions. The first direction is unmanned aerial vehicle. And here, in one of our papers, we studied UAV with positive and normal networks. So how UAV can be deployed in order to improve the performance in positive normal networks. So before going into the system model, so let me give some introductory about UAV. So UAV has many benefits. First of all, we can deploy UAV on demand, and can be very fast deployment. And then we can get access to inaccessible regions. Yeah, so if we need some connection in mining industry or in disaster areas, it can be a very good option to deploy. And also the good part of UV, it can provide line of sight channels. It can hover higher, it can move directions. And by doing so, you can find the optimal location where you can get line of sight communication with the user and improve the end-to-end delivery. And then the last one, yeah, because of its mobility, it can be employed in many places and solve the temporary solution as I said before. For example, let's say you have some event in one place and many people are gathered there. And in this case, the base station, fixed base station, cannot solve the problem. Congestion happens here. So in this case, UV can be a flying base station and offload some users not to guarantee the quality of service to all users that in that area. So the another method called coactive radio, which works for the spectrum. So there are two types of coactive radio methods, popular types. The first one is called overlay coactive radio. As you can see here, let's say you have this frequency band, this power density, and we can have primary users, we can have secondary users. Primary users means licensed users who pay for that study band. Secondary users, they're unlicensed users, but still they want to get access to that frequency band. Maybe they cannot use fully bands, but it's like opportunistic approach. And now in the network, we need to manage how we can provide the primary users, and at the same time, we can get some access to secondary users. And in overlay coactive radio, secondary users can coexist with the primary users at the same time, but they should share information between them. It makes hardware part of primary and secondary users more complicated, but still at the end we can get access to the entire bandwidth. The second method is called underlay. So primary users can transmit that frequency band. At the same time, secondary users also can get access to the primary frequency band. But as you can see, the transmit power of the secondary user is lower than the primary user. It means the primary users have some interference threshold. Yeah, so primary user says, okay, secondary users, you can use the spectrum band. However, the interference that you cause to my receivers should be below some level. If it's so, I can communicate easily without any problem with my quality of service, and also you can get access to the spectrum band. So this is underlay coactive radio method. And in our paper, we're going to use this method. And I'll elaborate there in more detail. And the third technique is called non-orthogonal multiple access, olma. So now let me compare olma with traditional orthogonal multiple access. In this case, it's FDMA, frequency division multiple access. So how FDMA works? In FDMA, you have this frequency band, and you have several users. You have 3 users here, and each user is allocated its own frequency band, the channel, the frequency channel. And they need to use the channel in a turn. So one user cannot get access to the entire frequency band. They allocate their own unique spectrum. However, in the NOMA case, non-orthogonal multiple access, all users can get access to the entire frequency. But in order to differentiate between them, they need to use different transmit power. By doing so, they can use the this entire band. And at the end of the day, they can double the usage of the spectrum. So by doing so, we can get to efficient spectrum utilization. And also, we can provide some user fairness for users. Because once you allocate the same band for each user, it can be that some of them requires high data rate, while the second one is IoT devices. Actually, that don't need much like data rate. But for normal, it requires small data rate, you can provide low transmit power. It requires high data rate, you can provide high transmit power. By doing so, you can be fair for all users. And also, NOMA provides you this enhanced connectivity, which is one requirement of 6G, massive connectivity. So if you apply NOMA methods, you can support many devices with the allocated spectrum. So now let me explain the system model that we worked on. We had the following system model where we have a primary network here, so with a primary base station that wants to serve primary users. And then at the same time, we have this hotspot. Inside the hotspot, we have several secondary users. And the secondary users need to get access to the channel of the primary. But they need to control their transmit power in order to cause interference to the primary users further underway cognitive approach. And also, we cluster users inside hotspot. In other words, if you have one primary channel, now you need to decide how many secondary users need to get access to that primary channel by using one. Then, as you can see, we have this blockage between secondary base station and secondary users. Therefore, to improve the signal quality, we use here UAV, flying UAV, and this UAV can hover around in order to relay the signal from secondary base station to the normal users. And here we need to optimize several parameters. Yeah? So we need to optimize this clustering, how many users need to be used in primary channels. Also, you need to optimize the power allocation for each user. Yeah, previously I said different user has different quality of service. And then also you need to optimize these phases of the hop, of relay hop. So this is the first phase, which is called broadcasting phase. And the second phase from UV to normal users is a relaying phase. And as it's working half duplex manner, we need to optimize the phase time allocation. And here is our problem optimization. So our aim is to maximize this auxiliary maximum rate variable, which is data rate. So we are going to use a maximum optimization, which means we are maximizing the minimum of data rate among the users, and then all of them get the same quality of service. So therefore, we need to first optimize this auxiliary maximum rate, and then all data rates of normal users should be equal to this sum. And therefore, we have several constraints. First constraint, all the secondary user rates are no less than the absolute variable here. Second, and the secondary constraint is here. Okay, the secondary constraint is each secondary user should belong, of course, to one cluster. Yeah, so if you have 10 normal users, you need to be sure that each user can be part of each cluster. And another constraint is the cluster size, which is also the number of primary channels must be less than n divided by k. N here is number of primary channels. Okay, n is number of normal users, k is number of primary channels. And the two constraints are here. Because of underlay cognitive radius, we need to guarantee that the interference constraint for primary user is below some predefined threshold. Otherwise, we can cause problem to primary users. And because of that, in two phases, phase 1 and phase 2, we need to provide some constraints. And the last one is variable domains. So see here is a cabinets, 3D cabinets of UV. At that we're going to optimize the location of UV, how it's optimal located to provide the best solution for the network data rates. And also here our optimization parameters, size, phase, and power allocation for normal users for two phases. And as you can see, we have several variables, some of them integer, some of them are not integer. Therefore, the problem becomes mixed integer nonlinear programming, which is becomes a hard problem. Therefore, we need to decompose the problem into several sub-problems. And then the problem becomes 3 sub-problems. And the first problem is resource allocation. In terms of this alpha, beta, and lambda, alpha is power allocation in the first phase, beta is power allocation in the second phase from using to normal users, and lambda is phase time allocation of the two phases. So alpha, beta, and lambdas we can find in a closed form by using analytical solutions. And then once we've found these analytical solutions, we use this information and provide it to second problem called clustering by knowing their gammas, which is SMR of each users. We can cluster them to each primary channels. And then once you find the clustering, all information go to, in terms of data rate, go to the third problem, which is about UV deployment. Here, we find the optimal coordinates in terms of x, y, z. And if you satisfy the all condition is problem 1 and problem 2, the location of UV will be the optimal. First of all, before the optimization, we did some research about the path loss for each phase. And here we have this secondary base station, we have this hotspot, normal users located inside, and we have hovering UV. Once here you have 2 holes. In the first hole, path loss is lower when UV comes closer to secondary base station because of line of sight communication, because of distance. And in the second phase, the path loss is lower once UV comes closer to the center of the hotspot. Therefore, in our searching algorithm, we need to provide location to UV and we decided from the edge of the hotspot, somehow closer to the hotspot and not far away from the base station. Therefore, in the algorithm, you use particle swarm optimization and simulated annealing methods. So there's two results. It's about the power allocation for normal users, how optimal they are, and how they can be changed for different kind of cluster. And here we find closed form solution for phase time factor. And here we prove that once each phase allocated equal time slots, that is the best option to improve the max mean throughput. And regarding the UV deployment, you can see that here we have a height of the UV from the ground. Here we have the distance of the UV from secondary base station to normal users. And once UV follows around, we found that the optimal location for UV 380 meters away from the base station, which is actually close to the center of the hotel. And the height should be 80 meters from the ground. And once the height of UV closer to the ground, the data rate gets degraded because of non-line-of-sight communication. You can see that in the scenario, you can see the real urban areas with buildings. So in this case, because of these obstacles, we enter into a non-line-of-sight communication scenario. So to get a line-of-sight scenario, we need to just add some height to the UV. Once you get higher than 80 meters, because of free space pass loss, again, you increase the pass loss and get a worse result in terms of data rate. And then we started our optimization from different locations of the UV. So first we put location of origin of the XY that traffic, which is close to base station. Then use different scenarios and also put UV at hotspot edge. And then you can see that once you put UV at hotspot edge, the convergence of algorithm becomes faster. So that was topic about using UV. Now let's talk about the configurable intelligent surfaces and how RAS can be used for normal users, also how it can be used to remove self-interference in full duplex networks. So brief overview of RAS. RAS can be used to control the wave of the millimeter wave or any frequencies. And the beauty of RAS is to control of propagation environment. And because of that, it can be energy efficiency because RAS you can use passive elements, yeah, no any amplification, not any extra source is needed to improve the signal. We just play with the phases of signals and create beamforming into one direction. And therefore, this is good candidate to use in 5G, and it can support high data rate. So in this system model, we used RAS, we fetched it building, and we have to ask the users they need to use olma protocol. And the idea is we going to send signal from each user to the base station. And because of buildings in the city, we need to use RAS as a relay surface to get better signal at base station. RAS has two sections, divided into two sections, N and M. These M elements, they are passive elements. The red elements, they are active elements. it can be built in different manner. Yeah? It can be totally active by having some transmit source, or it can be totally passive, only reflecting signal, or it can be semi-active. Half part can be active, half part can be passive. And the idea behind having this kind of active and passive elements because of normal approach. In normal, I said that users should have different power levels to be detected and station. Therefore, once two users can send signal through RLS, the user one sends through passive elements and it gets some improvement of signal. However, the red user, which sends signal through active elements, get better improvement of signal because of amplification. And in base station, it receives signal from two users. It's called superimposed signal. They receive at the same time, but it can distinguish between them because of power level. So, in the result of this work, actually we provided some improvement in terms of outage probability and the error rates. And then also we compared the normal method, this normal method with traditional olma method, and showed that olma provides better results. Also, we compared system with more passive elements, and also in this case, these active elements provide some improvement because of the activity. The one thing that we didn't do here is comparing energy efficiency, because they use active elements and actually they use some extra power to improve the signal. So here should be some trade-off between the energy efficiency and the data rate improvements. So now let me move to the next slide. So I'm going to talk about how full Douglas communication can be used with RLS, because RLS is also considered as a full Douglas communication. So what is full Douglas communication? In traditional communication, mostly we use half Douglas, yeah? Which means that each user either should send signal or the receive at the same time. They cannot receive and transmit signal at the same time because of humans. And in full Douglas, we say that each user, each antenna, let's say, can receive the signal at the same time and they can transmit the signal at the same time as well. But actually, by doing so, we can double the spectrum efficiency. We can reduce the latency because we transmit 2 times faster compared with half duplex, which can double the spectrum efficiency, which can enhance network throughput at the end of the day. However, all these benefits come with some challenges. And the main challenge is called self-interference cancellation. Once the user transmits signal and the receiver at the same time receives some interference. Sorry. It receives some interference, and that interference, the level of interference is very huge, which outperforms the level of signal. And when you calculate signal to interference to noise ratio, the level of signal will be lower than the interference, and you cannot get any signal. And in the literature, there are many techniques that can solve this problem. You try to fill the distance between transmitter and receiver, or you put some shield between them, so don't cause any leakage from the transmitter. Also, there are several analog cancellation techniques which try to cancel the self-interference and also the digital cancellation. Now, in our paper, we proposed one method, which is RIS. cancel this self-interference here. So here you have this full booklet base station. Then you have two users, download user and upload user. And here you also use arrays called star arrays. Simultaneous transmit and receive arrays. So these arrays can reflect the signal and also get the signal through download user located indoor, upload user located outside the building. The arrays can get signal through download user and also reflect the upload user. And each these elements has these parameters, changing parameters to adopt a reason for we use star arrays to improve the signal quality from download and upload user. Now, base station receives the signal from upload user to reflect into receiver of base station. At the same time, the transmitter antenna of the base station transmits signal to this indoor output user in the star array. And here we have this full duplex base station. And the key is transmitting signal at the same time for leakage to the receiver. It's all receiver. And it's called digital interference. Now we propose to use passive arrays or conventional arrays. So the same leakage signal from transmitter and the reflected arrays comes back to the receiver. So it's up to us how to manipulate phase shifters of arrays. So in this case, we align arrays elements, phases of arrays elements in such a way to cancel out these self-interference. So this is passive self-interference cancellation without using any hardware beside arrays. So now let's go to some mathematical parts. This equation that receiver, base station receiver receives from the upload user and from the interference. So first of all, base station receives an upload signal of interference from upload user. Then it receives self-interference from transmitter or from its transmitter and from upload. And then you have AWG noise. Now let's get into what is signal interference. Yeah? So we have this cascaded channel from upload user to the base station. Then we have the phases, and also we have the phase of arrays, star arrays. So we can optimize this phase of star arrays in order to optimize this part to make the level of signal interference higher. And regarding self-interference, so we have it consists of two signals. Signal from transmitter antenna, loop self-interference, and the signal reflected from the arrays. So our aim is to minimize this part. So this is actually what we receive, but we can manipulate with this channel from arrays. And if you write the SIMR of uplink receiver, you can see you have signal interference, denominator, signal power, and you have interference, you have noise. So we can do nothing with noise, it's given, but we can play with this part, we can optimize this part by changing phases of the RIS. So now how we can is to maximize data rate for the uplink. have several constraints. We are trying to maximize data rate of our user, but at the same time, we need to guarantee some quality of service for the output. Don't suffer from and then also, we also have some data rate threshold for the download. The minimum data rate threshold, and then we can start to maximize it from that point. And also another constraint, our power of self-interference should be below or equal to most power. Okay? So if you go to the previous slide, so this is power of self-interference, and if you make it smaller up to noise level, it becomes not SA, it becomes SNR, signal to noise ratio, so we don't care about self-interference anymore. Then we can improve the data rate. And then we have some constraints in terms of our motion of these elements, which should be between 0 and 1, phrases from conventional arrays from 0 to 2.5, and the phrases of arrays are the same. So actually what we get here, so joint optimization of arrays and star arrays can provide us, can boost interference mitigation and data rate at the same time. And in the results, simulated results actually, we observed several findings. So first of all, let's say we have this kind of dashed black lines. This is linked self-interference from the full duplex transmitter to the full duplex receiver, as you can see. If you have this 0 dB BM transmit power, you have leakage self-interference at level of close to minus 40 dB. And in the first experiment, we said, okay, let's put these elements, phases of these elements in a random manner. So array is not optimized. And as you can see, the level of self-interference is the same. Not any impact from arrays. Then we started to optimize arrays by providing some element, by increasing the number of these elements. And once we have up to 90 element arrays, the level of this, the level of interference is close to the noise flow level. So by doing so, actually we optimize self-interference, we minimize self-interference up to noise floor. However, once we increase transmit power of the duplex transmitter to 30 dBm, now we have higher self-interference level. But somehow still we can minimize it, but we couldn't go to the noise level, even if we increase number of segments. And this happened because of this called overshooting. Once transmit power and base station is in higher level, yeah, the magnitude of signal becomes higher. And now to cancel the same signal with arrays, the magnitude of arrays should be at the same level. So then we understand that one more consideration, optimization is needed in terms of the location of arrays. How far is arrays from the full duplex base station? If it gets further away, cancellation becomes not visible. If you come closer to arrays, you can get access to more better optimization. So this kind of trade-off should be considered in future research. And the second result, here we see how increased number of these elements provides improved data rate of the download user. And as you can see here, the data rate of secondary upload user is the same because we put constraint. We say data rate, the threshold for data rate is 2 megabit, 10 megabit, and 20 megabit per second. Once the algorithm obtains this data rate level, it starts working on improvement of data rate of download. Okay, so this is how we worked ROS in full duplets. Now, similarly, ROS can be used for physical layer security. So what is physical layer security? This is additional security level which can be done in physical layer, which can be used in addition to crypto security. But here we can manipulate the characteristics of the physical layer in order to provide secure connection to the required users. And there are different techniques how we can attain physical layer security. The first one is using artificial noise. So base station can send create artificial noise and send to unlicensed users or eavesdroppers to jam their received signal. Or you can use beamforming techniques. Yeah? You can direct beamforming into required direction to the licensed user. At the same time, send a beam steering, nulling to the eavesdropper. So the main performance metrics in physical layer security is called secrecy capacity, which is a difference of the data rate of, let's say, licensed users and eavesdroppers. But if the difference is higher, it means we get better, higher secrecy capacity. So in this system model, we consider base station, called else, we consider the licensed user, we call it log, and you have a bunch of licensed eavesdroppers who wants to capture the signal from the base station. And we consider the worst case scenario where the block is located further away from the base station. Also, it has some obstacle. We cannot direct signal from else. Therefore, fine areas. The purpose of the UV is to generate artificial noise. You can generate artificial noise and refer to through arrays elements. Now, arrays has two purposes. The first one is to relay signal from the Alice to the base station. So we separate arrays into several parts. The blue elements relay signal from Alice to log. And then we have several sectors for eavesdroppers. And each sector, they work directly, they create big beams directly to each eavesdroppers in order to jam using artificial noise sent by So as you can see from the system model, this eavesdropper, like it goes to Alice, has better signal quality than the location. Once it has high artificial noise, and by the UV, we can increase its received signal. We can decrease SIMR. In this case, interference in the SIMR becomes higher than the signal, and at the end, it cannot record the kill signal. So here the same, we optimized the location of UV, we optimized the number of these elements that need to work for each user. And then the problem divided into two parts. The first part is partition optimization. How many elements should work to each user? Here we find four solutions for putting SNR of each user, each eavesdropper and block. I find optimal base allocation. I find distance and calculate the secrecy capacity from that equation and provide that information as a secrecy capacity fitness function to RIS civil deployment. Where RIS should be located in order to provide optimal. And in the result, we had different scenarios. So first, we have this triangle, red triangle, which is one is proper, nothing further to the base station, and here is our work. And in this case, the optimization of areas is further to base station. It should hover just above the base station to get a line of sight communication and to jump a single example. Then similarly, if eavesdroppers like exposure to base station, optimal placement for the network or to that base station, once eavesdroppers gets exposure to both, now we become exposed to both. So, there is a trade-off where the eavesdroppers are located. And the good thing is, the good part of that is UV is mobile. It can hover to different places in order to optimize the sequence capacity. And here we use two optimization methods called particles one optimization and in our scenario, mostly simulate annealing provided better results by providing good convergence time, let's say here 0.6 seconds, and the maximum of I guess 0.64 seconds. Even it has many iterations than PSO, the convergence time is faster. And this good convergence time was achieved because of provided closed form solutions in terms of these RAS portions. Now, the last system model, again, RAS PLS, can be showed here. So this is joint project with Professor Ashram Hussain from Megapol University. Here, we said, okay, what happens if you don't know any channel information of the or location of the eavesdropper? Actually, it's very difficult to find the location or channel information of eavesdropper because they're passive. They don't provide any signal. You just hide somewhere and just capture the signal. So they are passive. You cannot get the location. You cannot get the information. So in this case, let's say you have this ball here, and the ball can be surrounded by some eavesdroppers in certain area. Now, Box wants to communicate with the else that probably doing it says absent signal. So the call of signal, and at the same time, else in a full duplex manner can send artificial noise. So the idea of artificial noise is to use some art of arrays. Here, arrays can create kind of beam steering. Take several beams, and these beams can shoot special location inside the cell. But in other words, we can cover the circle by beams with artificial noise. The idea is once this eavesdropper wants to capture the signal from the wall, we should that eavesdropper with RFB, the signal between. And the third collaboration, if there and by doing so, we get pretty good results. So we call it protected zone. And in the results, you can see we compare three methods. When we use only risk to jump to provide sequence capacity, and then we use one method where we only have artificial noise without RAS, so base station sends artificial noise directly to that zone, and the proposed risk plus artificial noise. And as you can see in the results, our method with arrays plus artificial noise has good security capacity, while the second and third method, they have lower. As a result, the security capacity of the proposed method improved approximately by 81%, which is quite good security capacity performance for the network. And this is more practical method because it can be used once you don't know the location of eavesdroppers, but you want to make secure communication for the required users. So these are some research directions of our research group. And also, as I mentioned before, we also work with fluid antenna systems. We also work with integrated sensing and communication networks, which are very promising technologies that can be used in 6G. So thank you very much for having attention. So if you have any questions, please. You're welcome. Any questions? I think interesting.
First of all, thank you for this enthusiastic presentation and taking us for this journey. So, as a new person, as it's also a new person to pilot communication, I hear a lot of information. So, first of all, I got a lot of questions. We're going to go over the questions, but I don't have any intention to make this so I'm starting from the last questions and the time terms. I'd like to ask another questions. So, but the last one, you told us, sir, that both actually we protect, actually we give some noise signals in an area so that we can have some security. But how do we ensure that Bob is not going to receive noise signals?
So in that case, Bob should know the artificial noise. And actually, it's like before communication shares information with base station. Bob should know the artificial noise information. So it can be called, it's like a normal protocol. How normal protocol works. Both users get sent to the host signal. And then each user should know about that information, so they can call signal and record it in second stage to call its own signal. The same model can be implemented here as well, but as I said, Bob should know the artificial.
Yeah, it's a great point actually. But then there's a question. The power of these noise signals comparable with the main signal power? If I'm mistaken, please correct me, sir. I'm just trying to figure it out. So I'll be going for another question from this point, because the next question I was asking was actually a person has a bad intention to decrypt signals. Maybe he or she can, decrypt the cipher by using some Fourier transform techniques so that signals can be separated frequencies, so that maybe some power and information can help for them to distinguish the main signals and the wave signals. So this is my bad idea to get around the issues actually, but if I'm mistaken, please correct me, sir. I'm just thinking on the street level.
Oh, so
do you understand my question?
So you have the power level of artificial noise and signals.
Yeah.
So this is a function of optimization. So if you know the location of Bob, so here, if you know the location of Bob, you can estimate the SNR or SNR of each user located at any point of the circle. For example, if you assume that the drop is landing here, you know the distance from L to the drop You know the distance from RS to the droplet. You can calculate the SMR. And then you need to give some threshold for the SNR of if. But if the threshold is, let's say, 0.1 megabit per second, and if you think that this kind of level, data rate, is not enough to capture important information from the signal, then adapt the power of artificial noise. You don't need to send too much artificial noise, because it's also about energy efficiency. So this is parameter of, this is a function of optimization level. So this artificial noise actually generated, this is signal. Artificial noise is signal, just randomly generated signal. If you don't know that signal, you can do nothing. That is the idea of this artificial noise. If you know the signal, we can detect it. So therefore, as I say, we have one assumption that both should know about that. If also both doesn't know the signal, he's in trouble.
So what I understand is the frequency of these signals are pretty close to each other, or not?
It can be at the same frequency.
It can be the same. Okay.
So the code and order can be different.
So
you manipulate this signal. So once let's say once both and the answer come together, they need to decide about decoding order, decoding mode. They need to decide about channel state information, what is channel state information. All this information will be shared with each other. And also artificial noise can be shared with both. It should be shared with each daughter. If it's true, then no problem. The method works.
My peers ask more questions. Other questions, I will be waiting for.
Yeah, your question is practical. Yeah, it's practical.
Yeah, I'm
the concept, mostly theoretical concept. Yeah.
Yeah.
Which works in theoretical, but yeah.
Yeah,
practical.
I think future. Yeah. I need to make some progress.
Yeah, sure. Thank you for the question. Please, any questions?
For self-interference cancellation, again, I'm going to ask for practical perspective. I must spare what about so it's is it like very practical or also mobile scenarios like the users are moving?
For self-interference cancellation, we use RLS.
Yes.
There's one paper practical. They use RLS to cancel the self-interference, but it was stack-based mission some RLS. For mobile, it's not easy because problem comes with channel state information. If you have precise channel information, if you have problem with channel state information, because how to say, difficulty of RLS, it's not only for self-interference, but still lower.
So IS configuration.
Yeah, it should be changed every because its phase changes. And the thing is, the good part is because there is full movement base station in the stack channel. And it's self-interference because of short distance. The mean power is almost same. Phase is also same. So once you can configure RLS for that phases, this the base station is mobile. But if you full loop with this mobile user, yeah. Any questions? Okay, thank you very much.
Thank you so much.